Hello friends, welcome to my channel. This is ISRO Vibration Paper 5, Part 5. Question is, a torsion bar with a spring constant K is caught into n equal lengths. The spring constant for each portion would be how much? So, we will use that formula already discussed. K equal to G d to the power 4 by 64 RQN. In this case, K is equal to stiffness of the spring, G is modulus of rigidity, small d is spring wear diameter, and capital R is coil radius, and N is number of turns. In this case, spring is caught into n equal length. So, K, everything is unchanged, only equal length, n equal length, so it's n by n. So, n into G to the power 4 by 64 RQN, or this is K dash, n into K. K dash is n into K. From option, spring constant for each portion would be A. A is our answer. N into K. Next is logarithmic decrement of a damped single degree of freedom system is delta. If stiffness of the spring is doubled and mass is made half, then logarithmic decrement of the new system will be equal to how much? So here, in first case, logarithmic decrement is delta 1. It's delta. We know delta formula is 2 pi zeta. This one already discussed. And zeta is C by Cc. And stiffness of first case is K1 equal to K. And in second case is doubled, so it's 2K. Let mass in first case is m, second case it's halved, so m2 is m by 2. Here C is not changing, only we have to check Cc. 2m omega n, 2m into root over of K by m, so it's 2K into m. First case is Cc1 is 2 root over of K by m, and in second case Cc2 is 2 into K is doubled and m is halved, so it's m by 2. Here it's K into m. Cc is, here we got 2 into root over of K into m. So Cc1 first case is Cc equal to K into m. In second case Cc2 is 2 into K is doubled and m is halved, so 2 to cancel, it's Km, same as Cc1 or Cc. Zeta is equal to C by Cc, and we already got Cc1 equal to Cc2 equal to Cc. So zeta 1 we have to calculate C by Cc1, and zeta 2 is C by Cc2. C is not changing, damping constant. So here C by Cc1. Cc1 equal to Cc2, it's C by Cc. So zeta is unchanging, zeta 1 equal to zeta 2, and we know delta equal to 2 pi zeta by 1 minus zeta square root over. Here zeta is not changing, 2 pi also constant, so delta 1 equal to delta 2 equal to delta. From option I have to check B is our answer. The difference in the potential energies between two arbitrary positions downward displacement x1 and x2. x2 is greater than x1. I will draw the figure. This is the figure. This is position 1 and position 2. Here displacement x1 and x2, and we know potential energy is half k x square. So x2 is x1 here given. The difference in potential energy I have to calculate, Pe2 minus Pe1. So half k x2 square minus at position 2 k x1 square, half k common, x2 square minus x1 square. It is the difference between two. So from option half k x2 square minus x1 square, B is our answer. Next, determine M equivalent and K equivalent for the system in below figure when x, capital X, the downward displacement of the block measured from the system's equilibrium position, is used as the generalized coordinate. Take I as moment of inertia of the wheel. We have to calculate stiffness equivalent and mass equivalent. So this is parallel condition. So K equivalent is K1 plus K2. K1 is 2K plus K, it's 3K. K equivalent we got from option D, not possible. So we have to go for M equivalent. Here we will do kinetic energy for translation plus kinetic energy translation for this mass and kinetic energy for rotation for this wheel or whatever it may be, not mentioned. Rotational kinetic energy plus translation kinetic energy. So it's half mv square plus rotational kinetic energy is half I omega square. And here x is our displacement and x dot is our velocity, x double dot is our acceleration. And one more thing we know, v equal to r into omega. Omega is the angular velocity. So omega equal to v by r. V already we got, x dot by r. R is the radius. So these things we will put here, half into m into x dot square plus half into I. Omega is x dot by r square. So half m x dot square plus half I x dot square divided by r square. Here take common half x dot square m plus I by r square. So it's like half mv square x dot square. So here it's m equivalent. M equivalent is small m plus I by r square. This is our answer from option m plus I by r square. B not possible. D already omitted. C also not possible. A is our answer. K equivalent equal to 3k and m equivalent equal to m plus I by r square. So B, A is our answer. The system described by the following governing equation of motion will have how many natural frequencies? Here we know natural frequency is equal to number of eigenvalues of the matrix, and in this case matrix is having order 2 cross 2, so number of eigenvalues is 2. So number of natural frequencies is 2. From option C is our answer. Find out the correct free body diagram for the middle mass for the given spring mass system in below figure. It will come for this middle mass we have to calculate. Here in option 1 it's x1 minus x2, so not possible. Here C x2 minus x3, so C also not possible. Here it's x1 minus x2, so D also not possible. Only option left B, x1 minus x2 correct, and x3 minus x2, this one also correct. So B is our answer. For what value of m mass will resonance occur for the spring mass system given below with the given spring constant? We have to count mass for resonance condition. Mass how much we have to calculate. So given F equal to Fo sin omega t, so Fo equal to 200 and omega equal to 50, and K equivalent stiffness, this is parallel condition, so 2 plus 1 it's 3 into 10 to the power 5 Newton per meter. At resonance omega n equal to omega c, so we have to calculate omega given, no? So here we will find omega c equal to omega n, it's 50 equal to K equivalent by m root over. K equivalent we have to find 3 into 10 to the power 5 divided by m is 50 kg. So it's no, m is not given, m we have to calculate. So squaring both sides, 50 into 50 equal to 3 into 10 to the power 5 by m. So m equal to 3 into 10 to the power 5 is 1000 into 100 by 50 into 50, 0 0 cancel, 5 into 5 is 25. It's 40. 40 into 3 is mass is 120 kg. This is our answer. From option D is our answer. As shown in the figure, a mass of 100 kg is held between two springs. The natural frequency of vibration of the system. This one already discussed. It's a parallel condition. So K equivalent equal to K1 plus K2. 20 plus 20 is 40 kilonewton per meter, or 40 into 10 to the power 3 Newton per meter. This is K equivalent. And mass is 100 kg. We have to calculate in cycles per second. So Fn equal to omega n by 2 pi. It's 1 by 2 pi into K equivalent by m. So 1 by 2 pi, K equivalent is 40 into 10 to the power 3 divided by m is 100 kg. So it's 10, 400 root over is 20 by 2 pi. It's 10 by 5. It's in cycle per second or hertz, natural frequency. So from option C is our answer. The reading of a spring balance is from 0 to 200 Newton is 10 cm long. A body suspended from the spring balance is observed to oscillate vertically at 2 Hz. The mass of the body is nearly how much? Weight given W equal to W or force equal to 200 Newton, and delta is 10 cm. It's 0.1 meter. Fn is 2 Hz or 2 cycles per second. The mass of the body we have to calculate, and we know K is W by delta. From here K equal to W is 200 by delta is 0.1, so it's 2000 Newton per meter. So Fn equal to 1 by 2 pi K equivalent by m. So Fn is 2 pi K equivalent is 2000 by m. It's 4 pi 2000 by m root over. Then squaring, it's 16 pi square equal to 2000 by m. So m equal to 2000 divided by 16 into approximation we have to do 3.14 into 3.14. So by 4 by 4, it's 4 here, 500, then 125. It's 125 by 3.14 square, nearly 10. So it's m equal to 12.5 kg approximately. From option B is our answer. This is end of vibration paper. Thank you.